Yeah, welcome everyone to the Guaranteed Safe AI seminars. I'm Orpheus. This is essentially a monthly, ideally, series on AI systems with quantitative safety guarantees. And today we have the pleasure to have Lars Lindemann, affiliated with ETH Zurich, with a talk entitled Verifiable AI-Enabled Autonomous Systems with Conformal Prediction. The session is a bit less than an hour, and absolutely feel free to ask clarifying questions during the presentation, and we'll have time, at the end for a deeper discussion. So yeah, without further ado, thanks so much for being here, Lars, and everyone that is here. And yeah, let's do it.
That's good. Thank you so much for the invitation. Of course, very much appreciated. Yeah, like it was already said, I'm going to talk about verifiable AI-enabled autonomous systems with conformal prediction. And with this talk, I have mainly three goals. First of all, I would like to tell you about conformal prediction, which is a statistical tool for uncertainty quantification that has become quite popular over the last years. And second, I then want to show you how we can use conformal prediction for control design of AI-enabled autonomous systems. And in the third part, I want to show you how we can do predictive runtime verification of AI-enabled systems. First of all, though, what are autonomous systems? Well, at the end of the day, these are control systems that operate autonomously in complex and open-ended environments. And the research in my lab is particularly motivated by applications in autonomous driving and robotics, but more recently also in wildfire prevention, or more generally in disaster recovery. But there are many more. Maybe some of you work on these. Oops, that was too fast. For instance, in space exploration, in warehouses, agriculture, or even smart cities. And I think all of these examples here certainly highlight the importance and the potential impact that autonomous systems research can and will have in the future. What we've seen specifically over the last years is an increase in the available of data and compute. And this has really led to an acceleration of the progress that we have made in order to build these autonomous systems. I've shown three examples here. There are many more, for instance, Boston Dynamics robots or Tesla cars or even drone fleets that really accomplish highly challenging tasks with ease. However, the question that I would like to ask you and that I'll ask in my lab is, do you think that we really have all the theories and tools in hand to build autonomous systems that are also safe? And I would argue that the answer is obviously no, because at the same time, we've seen a lot of failed demonstrations. We've seen Boston Dynamics robots crashing. We've seen Tesla or other self-driving cars colliding. And we've also seen drone fleets collapsing. So the answer really is a clear no. Nonetheless, we have moved ahead and we have still deployed these systems in the real world, but not surprisingly, we're still facing issues. For instance, here, a Waymo car that was passing by a police standoff where a criminal was being apprehended. Certainly something that we really don't want to see. And another example here where a food delivery robot collided with a disabled man in a wheelchair. And yet another video here where you can see a robot headbutting a person in the crowd. So really a clear safety issue. Now, there are many more videos on the internet. That's not really the point. The point is that we should start, and we actually do this, we should start more seriously thinking about what are the reasons why we're facing these challenges. And there are certainly many, but I want to focus on today mainly three. One, and that's motivating the seminar series here, is that we're using increasingly more AI. And as you know, AI models can be quite complex. And for that reason, be really difficult to reason over in terms of their safety. And that's referred to here as the AI's Achilles heel. Another one are so-called distribution shifts, which on a high level mean that the conditions during deployment and design time may be different. For instance, we may be using data from sunny weather to train our system, but now we may want to deploy it during rain or snowy conditions. And yet another big issue is interaction between systems, for instance, between pedestrians and in this case, self-driving cars, where interaction usually is hard to model and also for that reason difficult to reason over in terms of safety. Now, talking a bit more about AI-enabled systems, we like to think of those in terms of block diagrams, and I have a very abstract one here for you. We have here a dynamical system. In this case, this is a car. We also have an environment that may be other pedestrians or other cars. In general, this is uncertain and maybe dynamic. And usually we have sensors. In this case, we may have camera or LiDAR data, right? And what we typically do is we use this sensor information and push it through perception and prediction algorithms to get state estimates. So estimates about the state of the car and the environment. And we then use this information for planning and control to feed back control inputs to the car. And we may be doing this over and over again. Now, where do we have AI components here in this loop? For instance, we may use AI for detecting objects in the environment and for assigning semantic labels. But we may also use AI for trajectory prediction. For instance, we may be predicting pedestrians at an intersection. Or we may be using AI for modeling systems or directly for getting decisions. And while this slide here really is tailored to autonomous driving, you can make the same case for wildfire prevention if you want, where you want to detect fires, you want to predict their spread over time, and you may want to use drones to mitigate fires. Having these AI-enabled systems then raises several questions. For us, most importantly, the one that I want to raise is, how do we reason about safety of such high-dimensional systems? And by high-dimensional, I mean that we may have really AI models here for perception and prediction, for instance. So just to make an example, a feed-forward neural network that may consist of thousands of neurons, or maybe even more complex AI models. Now, there has been existing work, I believe here in the workshop, this has also been discussed, about methods that can quantify input-output behavior of, let's say, neural networks or neural network control systems. For instance, there are exact techniques such as satisfiability modular theory solver or mixed integer linear programming techniques to do exactly that. However, these techniques have scalability issues typically, and they don't apply to the complexity of the problem in hand. And this has motivated a lot of research looking into convex relaxations of these formulations, for instance, using semi-definite or linear programming approaches. But here the issue really is that these are too conservative to be applicable for these type of problems. Now, ideally, what we'd like to do is we'd like to navigate this trade-off between scalability and conservatism, and we would importantly also like to reason over randomness and uncertainty that enters this autonomy loop. For instance, disturbances on the system, noise on the sensors, or generally randomness in the environment. And that's when we started asking ourselves if we can instead use more efficient statistical tools to reason about safety. And what I want to argue here in this talk today is that what we need to add into this autonomy loop is an online monitor that performs uncertainty representation using efficient statistical abstractions. And as we will see, these statistical abstractions we can build or construct with this tool called conformal prediction. And that's what I want to tell you a bit more about now. So I'll give you a crash course in conformal prediction. It's become quite popular over the last years, as I mentioned before, because it can do uncertainty quantification under minimal assumption. To begin with, it's distribution free. So assume that we're in a supervised learning setting where we have inputs U and outputs Z that may be drawn from a distribution calligraphic D, then we don't need to make any assumption on this distribution. It doesn't have to be Gaussian, it could be any funky distribution. At the same time, we also don't need to make any assumptions about predictors that we're using. For instance, if we have a predictor mu that takes an input u and predicts an output z hat, this could, for instance, be a neural network or even something more complex if you wanted to. It could also be a physics-based model. What you, however, need in this vanilla setting is the availability of an IID, so independent and identically distributed calibration data set of input-output pairs that also come from this distribution. And the goal in conformal prediction then is the following. You as a user fix the failure probability delta. So you pick that. And conformal prediction gives you a region C such that for a new test data point, the output is contained in this region C that may depend on the test input with a probability no less than 1 minus delta. Just to illustrate this, assume you're given 3 images along with a classifier. Then this first image here is easy to classify. In this case, the prediction region may only contain 1, the correct label, while images 2 and 3 are more difficult to classify and for that reason have 4 or even 6 labels in this prediction set, simply quantifying the difficulty of the task in hand. So that's the high-level goal. How does conformal prediction work? Well, the vanilla version, so the simplest version, is based on a really trivial quantile lemma. That goes as follows. You assume here that you have k plus 1 IID random variables, denoted R0 to Rk, and people in the community refer to it as the nonconformity score, but you can just think of it as a prediction error if you like. And the goal then is to find a probabilistic upper bound of the test data point R0 in terms of the calibration data R1 to Rk. And what one can show is that with probability no less than 1 minus delta, the test data point R0 is bounded by the 1 minus delta quantile over the empirical distribution of the calibration data and infinity added. So what one technically has to do is one has to plot the histogram of the nonconformity score. So here you see the potential values of the nonconformity score on the x-axis and the frequency on the y-axis. Then you plot your calibration data here and you pick the 1 minus delta fraction of those. Now, if you really want to compute it in code, you do the following. You compute p, which is the ceiling of k plus 1 times 1 minus delta, and you pick the pth smallest nonconformity score. So all that you have to do is you have to run a sorting algorithm and pick the pth smallest score, and this is evidently computationally super efficient. You can do it while your autonomous system is operating. And you may wonder, well, how much data do I really need? There's an implicit data requirement. Since you pick the pth smallest score, p is not allowed to be greater than the total number k of data points. And you can even rewrite this a little, do a little math, and then you get an explicit bound for the number of data points, which is 1 minus delta over delta. Now I'm skipping a lot of details here, a lot of extensions of conformal prediction, but if you're interested in this after the talk, we've almost a year ago published a survey paper about this, where we have an introduction to conformal prediction, a lot of sidebars with additional information if you like. Okay. Now, I think why conformal prediction over the last years has become quite popular is because it gives you a lot of flexibility. So far, we have not talked about what this nonconformity score is, and you, as an engineer, have a lot of freedom to engineer it, to design it for the problem that you're interested in. Just to make a simple example, assume you're interested in a 1D regression case, then you can define the naive nonconformity score to be the absolute error between your output and your predicted output. And then you could apply conformal prediction to it, and you get that the error during test time is bounded by the 1 minus delta quantile over your calibration data. And in this case, you can even rewrite this further, this probabilistic guarantees, by getting a valid prediction region that is centered at your prediction and has a width of 2 times the 1 minus delta quantile, and it contains, with 1 minus delta probability, your test output Z. And I argue the conformal prediction is simple because it's really simple to understand, just the previous 2 slides. It's general because it applies to black box systems as long as you have data. And it's efficient if you're smart about choosing the right nonconformity score. And I want to give you 2 examples here. For instance, here we have this F-16 aircraft, and we wanted to predict the system states 2 seconds ahead in the future. And what you can see in black are test data points, so empirical data of your error. And then in orange, green, and blue, you see different shapes of prediction regions that were obtained from different nonconformity scores, and they all capture 95% of the test data here. You can even deal with multimodal data if you want to. For instance, here we have a robot that can go left, right, or straight with equal probability. Here in green, you can see test data, and you can see clearly 3 clusters which correspond to left, right, and straight to these modes. And in black, you can see ellipsoids that were fitted to this data and capture 95% of the data. Yeah. Okay, so I want to end this introduction with a small disclaimer, because oftentimes in the community and beyond, the conformal prediction guarantees are misinterpreted. We call these guarantees marginal because the probability measure here captures randomness in the draw over test and calibration data, so over R0 to Rk, all right? And this is in contrast to what we would ideally like to have, in which we call calibration conditional coverage. So a probability where we condition on our calibration data and where the probability only captures randomness over the test data. However, such guarantees, while desirable, are in general impossible to obtain without making strong distributional assumptions. But there are good news in the case when the nonconformity scores have a continuous distribution. We can interpret this conditional probability as a random variable that has a beta distribution that is centered at 1 minus delta, so exactly where we want it to be, and has a variance of 1 over k. So the more data we get, the more accurate we can obtain our ideal guarantees. There are other versions of how you can get these approximately, but that's kind of just to give you a high-level introduction. So now that we know about conformal prediction, I want to go ahead and I want to talk about safe control in dynamic environments. So what's the problem that we want to deal with? We would here like to compute control inputs for our control system so that it avoids dynamic agents in the environment with a probability of at least 1 minus delta, all right? So consider you want to control this car here, and it should avoid other cars and other pedestrians with 1 minus delta probability. Now, why is this a challenging problem? To begin with, we have to deal with uncertain and interactive agents that may have unknown intentions to us. And in practice, what one typically does is we're using learning-enabled, so AI-enabled predictors to predict their future behavior. But these predictors, they may not always be perfect. In fact, they're often quite imperfect. And what we need to do is we need to jointly reason over the uncertainty in the agents and the learning-enabled predictor and integrate them into our control design. Now, very briefly about existing work, there's a lot of work, especially in robotics, about vanilla motion planners using graph or sampling-based methods. However, these generally ignore the dynamics of the agents. Now, there's also a lot of work on reactive control methods using navigation functions, dynamic window approaches, or maybe some of you have heard of control barrier functions. However, these are reactive in nature, and for that reason, they don't use any predictions, and they typically apply to rather simple systems. And then there's a whole bunch of literature on predictive, interactive, and non-interactive methods, for instance, deep reinforcement learning, Gaussian process-based modeling and control, and so on. However, here I would argue that these typically don't provide you any strong safety guarantees unless you make simplifying assumptions again. And what we want to do now is we want to answer the question how we can quantify uncertainty of learning-enabled predictors and then use these for safe control design. Before going into the details, I want to give you a high-level overview of what is about to happen. We assume here that we have an offline trajectory dataset. For instance, assume that you've been at an intersection and you've observed how pedestrians walk over this intersection, right? Now, online, while the car is operating, we assume that we can measure the state of the pedestrian in this case at the current time, here denoted by y of t. This could be position, velocity, or other states. And we may even have a history of these states, okay? Then we're using a trajectory predictor. This could be a learned component, for instance, a recurrent neural network here in our work, to make predictions about the future behavior of the pedestrian, which we denote here by y hat of t plus 1, y hat of t plus 2, and so on. Now, the big question is, how good are these estimates really? Since we're using learned components, the estimates could be quite accurate, but they could also be far off, and that could be a safety issue for obvious reasons. And we have no way of knowing at this point if the estimate is good or not, and if it's safety critical or not. And for that reason, we're going to use conformal prediction, and we're going to compute, shown here in blue, these blue prediction regions that are statistically valid in the sense that they contain the future behavior of the pedestrian with 1 minus delta probability. And once we've computed these, we'll forward these to the dynamics of our system, in this case, a robot, where we assume that we know these dynamics and we design a safe controller. In this case, this will be a modeled predictive controller that makes sure that a safety constraint C that is defined over our system X and the dynamic agents Y is non-negative, for instance, to keep a minimum safety separation. And the method that I'm going to present is really computational lightweight. It comes with probabilistic safety guarantees, and we can even deal with distribution shifts, so when we have non-IID data, and we can also deal with temporal logic constraints, so with more complex specifications. But I'm not going to go into the details of this here today, but I'll briefly touch upon it. Okay, so now in order to address the problem, we need to model it carefully. Here, we model the dynamic agents as a random trajectory. And this looks as follows. The state of the dynamic agent at time 0 and 1 is drawn from this trajectory distribution, calligraphic D, which can be any discrete time stochastic process, for instance, an MDP. Importantly here now, it's static for now. So there's no interaction which would be modeled as a dependence on X, the trajectory of the control system. Then we consider a trajectory predictor that maps observation up until the current time into prediction of some until some finite mission horizon time, capital T. And for this here, we use social long short-term memory networks. So each agent in the environment has such an LSTM, and the weights are pooled together to model social interaction. And this is simply, there's an algorithm that we were able to download, and for us it worked really well. But I want to make the point that in general, we're model agnostic. So you could use generative models if you'd like, or even physics-based models if you wanted to. And now just to remind you, the task is to compute these blue prediction regions. Now, we have a couple of methods to do that, but I want to present one that worked particularly well for us. And what we do here in particular is we design a special nonconformity score. And the nonconformity score here is the maximum over all times tau that we're predicting into the future. And for each of these times tau in the future, we compute the prediction error, so the error between the state at time tau and the prediction at time tau, and we multiply it with some normalization constant that will make sure that we get minimum volume prediction regions. And if we define the nonconformity score like that, and we apply conformal prediction, so we compute this quantile, we immediately get multi-step prediction regions. So we know that for a new test trajectory, the tau step ahead prediction error is bounded by this quantile that is renormalized by alpha. And importantly, this holds for all times tau that are of interest to us. And I think this is well illustrated in an example. Here, for instance, we had a dynamical system that we predicted 20 steps into the future, shown in blue. And in green, you can see these cone-shaped prediction regions that get larger the more we predict into the future. And in red, I'm also showing a baseline method here that simply illustrates that other methods are more conservative. So we get efficient prediction regions that also give us minimum volume. And this is also illustrated if we look into 2D plots. Here, for instance, 1.25 seconds ahead. In blue, again, we see test errors. And in green, you see how we tightly capture 95% of the data. Now, very briefly, what I haven't told you about is how we choose these normalization constant. I told you we pick them in a way to get minimum volume prediction regions, and we obtain these as the solution of an optimization problem in which we enforce this nonconformity score, this max nonconformity score over our data. We minimize our 1 minus delta quantile, and we enforce some normalization budget that gives us a well-posed optimization problem. Now, if you think about this carefully, for you make two observations. First of all, this optimization problem, you can solve it offline, so you don't need to solve it while the system is operating. And second, it's a mixed integer linear complementarity problem, because the quantile operator here can be rewritten as an inner linear program. And this inner linear program, you can rewrite it using its KKT conditions, and this gives you so-called linear complementarity constraints. And the max operator here, you can simply rewrite it as a mixed integer linear program. There are also relaxations of this, but this is the high-level idea. Okay, so now that we have these valid prediction regions, we can go ahead and we can do control design. And in this case, we do a model predictive controller that at each time step observes the dynamic agents in the environment. It makes new predictions about their behavior. It recomputes the prediction regions, and then we solve this optimization problem at each time step. In particular, we want to find control actions that minimize a cost function subject to the dynamics of our system, subject to some input and potentially state constraints, and importantly, subject to some robust safety constraint. And in this constraint, we make sure that the safety function C is satisfied for all realizations of the dynamic agents in our blue prediction regions. All right, and this gives us 1 minus delta safety. Now, looking at this, we can note that this is again a bi-level optimization problem. There are different ways of reformulating this. For instance, if the constraint function C is Lipschitz continuous, you can have a closed form expression to reformulate this. Now, if this model predictive controller is recursively feasible, so if the optimization problem is feasible at each time step, we're guaranteed to find a safe controller with a probability of at least 1 minus delta. Recursive feasibility is, I would say, in general, in stochastic control an open problem. We looked at it from two angles. We have one way in a shrinking horizon formulation where the prediction horizon shrinks. We can formulate this constraint to formally ensure that we have recursive feasibility. And we also have ways of statistically quantifying the likelihood of being recursively feasible. But just some plots. Here we have a toy example. In this case, we have a mobile robot that should avoid these three dynamic agents. And what you can see here is that we built these cone-shaped prediction regions shown in green that shrink over time. They get smaller. And for that reason, the robot can plan an optimal path. We also implemented this in Carla, an autonomous driving simulator, where we have pedestrians that start at random positions, go to random goal positions, and have random velocities. And we empirically validated our statistical guarantees. For instance, here we were to at most have 5 safety violations, and in 100 runs, we only observed 1. What is also interesting is that we compare to Gaussian processes, which is a Bayesian approach, as you may know, and which here only had 70% coverage. And this, I think, illustrates the advantage of frequentist methods, such as conformal prediction, that you really get a frequentist interpretation as opposed to many Bayesian approaches. I also want to briefly talk about interaction between the control system and the dynamic agents in the environment. So the guiding question now is, what if interaction between the control system and the dynamic agents changes the distribution of the behavior of the dynamic agents? And just to give an example, this may happen, for instance, if the self-driving car here comes too closely to the pedestrian. You see the pedestrian here is halting for a second, or the pedestrian may also run away. And in this case, technically, all the safety guarantees that we derived before, they get thrown out of the window. You can quantify that these guarantees degrade gracefully, but you're not arriving at your initial 1 minus delta guarantees. And this is due to a chicken and egg problem where on the one hand side, you have your control system that is described by these dynamics. And on the other hand, you have your dynamic agents that are described by this distribution D that now depends on the trajectory of your control system, which can induce a distribution shift. So a change in the data that you may be receiving. At the same time, though, the control system depends on the dynamic agents through the controller, because the controller depends on the prediction regions, these blue regions, that is computed from data from your system. In other words, your dynamic agents depend on the control system, while the control system depends on the dynamic agents. And this creates a circular argument that makes it difficult to reason about safety of the system. And we were wondering here if we can iteratively update our controller to break this circularity. And I'm not going to go into details here, but I want to give you a high-level intuition for how this works. In this case, we again assume that we have our pedestrian here, and we again use a trajectory predictor to predict the future behavior of the pedestrian. But now, initially at the first episode, we assume that these prediction regions are incredibly large. So they are so large that, for instance, even if Usain Bolt was running, the predictions regions would be correct. Okay. And we say we have a radius of C0, so big, right? Since the radius is really big, we also know that the controller pi under this radius C0 is again safe with 1 minus delta probability. And because it's safe, we can go ahead, we can deploy the controller, and we can collect safely new data. And we could use this data together with conformal prediction in the next episode to update the radius of our prediction regions to C1. And hopefully this radius will be smaller and it will still be safe, leading to the fact that the controller under C1 is safe. And then we can go ahead, we can deploy the controller again, we can collect new data, we can recompute prediction regions, and hopefully we again get something smaller and safe, right? So we rinse and repeat this until our algorithm converges. And again, I'm not going to go into details here, but the idea is that we're using a robust version of conformal prediction to make sure that while we update these prediction regions with new data, that we're staying safe. And we also analyze convergence of this algorithm. So if you're interested in more details, check out this reference here. What I want to do instead is I want to use the remaining time to talk about predictive runtime verification, so the last part of this talk. The motivation here is as follows. We may have an AI-enabled system, for instance, an aircraft, we may have a self-driving car, or really any other system. And we would like to, while the system is operating, be predicting into the future and get an answer, a high confidence answer as to whether or not the system is safe. Okay. Now, the way we model the problem is as follows. We again consider discrete time stochastic systems. So now our system trajectory is again drawn from this distribution calligraphic D. And then the problem that we want to solve is the following. We are given observations of our system up until the current time t, and we would like to compute the probability that a safety function that is defined over the whole trajectory, so not only our observations, but the whole trajectory, is non-negative. And this raises various challenges and I would say questions. For instance, how do we really systematically express these safety requirements that are denoted here by raw phi? But also, how do we design efficient, so real-time capable, but also interpretable runtime monitors? And lastly, how do we equip them with statistical verification guarantees? So let's focus on the first question, how can we express safety requirements? Now, in various domains or fields, people express safety requirements differently. For instance, if we look at reinforcement learning, there's always the question of what is a good reward, right? We can tweak our reward to get good behavior, but this can lead to something called reward hacking, which you can see here, something that maximizes the reward but does not give you the desired behavior. There's also a lot of work on learning from demonstrations. However, I feel the drawback here is we need to get good and high quality demonstrations, and often we need to get a lot of them. And now in this time and age, we have a lot of, or we use a lot of large language models, but here the common crux is what is the right prompt? And this again raises questions of how we can importantly unambiguously specify safety, how we can automatically verify and enforce safety requirements, and how we can deal with uncertainty. And what we're going to use here is so-called temporal logics, which provide a principled way and a mathematical way to express requirements. Now, I don't have the time to go into the syntax and semantics for those of you that are not familiar with temporal logics, but I want to give a high-level example of what you could be expressing using temporal logics. For instance, you could say that the drone here should always avoid region E. It should every hour inspect region A and B. Whenever the battery level is low, the drone should recharge eventually in C or D, and it should turn on communication within some time. Okay, so it's a very expressive specification mechanism that is close to natural language, actually. But importantly, every temporal logic formula phi, as we denoted here, has a safety function raw phi. So a real valued function that is positive if we satisfy the requirement and negative otherwise. And that means that every temporal logic requirement can be translated into such a safety function that we can use. And indeed, temporal logics have been used across various domains here, for instance, for formulating traffic rules. This is in German, the traffic laws in German traffic, but it's also been used in healthcare for pancreas monitoring or for monitoring smart cities. This is some work we did together with collaborators from Trina. And the cool thing right now is back in the days, you needed domain experts to write down temporal logic specifications, but now LLMs really enable an automatic interface. So you could just have a requirement that you write down in natural language in English, you feed it to an LLM, and the LLM may give you temporal logic specification that you can then use. So it's broadly applicable now. Okay, so now that we have these safety functions in temporal logic, how do we go ahead? Again, I want to give you a high-level overview. We assume here that we have an offline trajectory data set again, and we again make observations of the system until the current time t, of the state of the system up until the current time t. Then we again use a trajectory predictor, could again be a learned component, to make predictions about the future behavior of the system, which is denoted here by y hat of t plus 1 and y hat of t plus 2 and so on. And then we compute this safety function that we previously defined over the observations and the predictions that we've made. And now we can ask a similar question to before. How good are the estimates of the predictions, and how good are the estimates of the predictions of the safety function? And we will again design and use conformal prediction to get an answer to this question. Indeed, we will get a probabilistic lower bound for the unknown safety in terms of the predicted safety and a calibration constant C. Now, we propose two lightweight monitors, one, as I said, that is accurate and efficient, and another one that is interpretable, and all of these have, again, statistical safety guarantees. So let's start with the accurate algorithm that is conceptually also the simplest. As before, we consider observations and we consider predictions for a finite mission horizon T. In this case, we use a long short-term memory network again, but as said before, you could use generative models if you wanted to, or physics-based models. And then importantly, you define the non-conformity score to be the predicted safety minus the true safety. And you evaluate this non-conformity score over your calibration data, and you compute the 1 minus delta quantile using, again, conformal prediction. And you immediately get that for a test data point, the predicted minus the true safety is bounded by C, and you can then simply rewrite this and you get your desired guarantees as stated before. So you get your bound on your safety in terms of predicted safety and your calibration constant C. Now we validated this in Carla for learning-enabled lane-keeping controller. So the goal here is to keep the so-called cross-track error, so the distance between the center of the car and the center of the lane, as minimum as possible. We have an imitation learning controller here shown in blue, as well as a learned control barrier function shown in yellow. And what we did in these experiments was basically just finding out if we can really predict unsafe behavior and if we can even use the tool to find the safest controller. Now, in this case, we set the safety level to be 5%, so 95%, and we have two specifications for both controllers. The first one is overall safety, meaning that always after 10 seconds, so this is temporal logic, I'm translating this for you. So after 10 seconds, this cross-track error should be below 2.25. And we see here the calibration constants that we computed from our calibration data are larger for the imitation learning controller. And empirically, we also got our 95% coverage. So statistically, everything checks out. We also had a second specification for controller reactivity. Here we wanted that whenever the cross-track error becomes or goes above a certain threshold, it should eventually always go below that threshold. We computed these calibration constants, and we again found that statistically everything checked out. Now, the approach is sound, but also importantly, note that these calibration constants C can be used as a measure of uncertainty and trust during runtime to maybe decide what controller you may want to be operating. And this is great. So it really allows you to monitor in a predictive way safety. But what it does not tell you is it doesn't identify causes of violation. For instance, if you may get an alert for this controller, for instance, you don't know where and when and ultimately why the car is unsafe. And for that reason, we want to have interpretability. And what I'm going to present now has interpretability in the sense that we're again using these prediction regions, and that then allow us to backtrack which part of the specification, if we have complex logic specifications, is violated. So what we're using here is, again, we compute these prediction regions as in the second part of the talk. And then what we're simply doing is, at least conceptually, we're computing the worst case safety over all realizations of our system in the future in these blue prediction regions. And if we can compute this, we get the guarantee that the true but unknown safety is lower bounded by this worst case safety, again, with 1 minus delta probability. Now, this is very temporal logic specific, but we can, if we use temporal logics, we can actually compute this efficiently because we can compute the atomic elements, temporal logics, which are called predicates, effectively. If we've observed our state already, so if the time tau is in the past, we can simply compute our predicate. And if that's not the case, if the state is in the past that we're interested in, we're computing a worst case over these atomic predicates. And then in temporal logics, you usually have Boolean and temporal operators, and they are defined in the standard way. I know this may be a bit confusing because it's quite technical for people who are not into temporal logics, but what I'm saying here is we can compute this efficiently if we want to. Okay, just to wrap this up, we have an F16 case study here where we compare the accurate and the interpretable method. The interpretable method here, you see in this plot, you have 100 test trajectories, and in the color, you can see the predicted safety, while in gray, you see the true safety. And in this case, indeed, we get 100% coverage. And the accurate method here, you see, is much more accurate. The gap between the gray and the colored points is much less. And in this case, we get 69% safety. And this reveals kind of a trade-off. The interpretable method is conservative. The accurate one, as the name says, is accurate. But the interpretable method gives us way more information that lets us pinpoint potential safety issues. Both methods, though, don't need retraining if you change specifications. That's a big advantage. And generally, it's really easy to implement and understand. So if you want to implement this method, you can do this in just a few lines if you have the data available and your simulator. And with that, I want to, finish this talk, and I'd be happy to answer any questions if there are.
Awesome. Yeah. Round of applause for the presentation. Thanks so much. We have about 15 minutes for questions and discussion. Yeah, to do so, ideally, you can raise your hand. I do have a question, but let's go through everyone's questions first. Mustafa?
Okay, so first of all, is my voice clear?
Yes, we can hear you.
Okay, so I wonder, so for all the examples that you've shown us, all of them are related to mission critical environments. And I think the motivation is clear. We care about safety in such environments. But I wonder, do we use such statistical safety techniques in other environments? So for example, nowadays, everyone talks about agentic systems and their deployment in financial systems or the financial sector in general. So are you aware of any deployments or any utilization of statistical safety in domains beyond cyber physical domains, which are of interest to engineers in particular?
Yeah. You mentioned finance, and I think finance has a history of actually using uncertainty quantification tools and risk measures. There's a famous paper from Rockefeller in the 2000s that uses conditional value at risk. So I think in finance, probabilities or other kind of risk measures that reason over properties of a distribution are of interest, really. I personally focus on cyber physical systems because the motivation of safety there is clear. I'm not sure the other example that you mentioned, how this would look like if we talk about agentic AI. For me, if there's an embodied component, like a robot, then it would make sense again. But I'm not sure, yeah, if you have some agents that are doing some web services, if that's really needed there. Maybe if you want to increase performance, if there's an argument to be made about you want to achieve a certain performance, otherwise customers are not satisfied. But this is just me guessing. What I know is finance uses it a lot. I guess in self-driving cars, robotics, medical systems. There, it's evident that you use it. But that's the CPS kind of domain, right? Yeah.
Okay, another question. What about the public perception? So as far as I know, when it comes to autonomous vehicles, for example, stakeholders may still be very cautious from self-driving cars, and they have their own concerns. Okay, what if some accident happened? Whom should we blame? Do we blame the engineer or the dataset? Or so when it comes to the accountability problem, that is something that I still find unresolved up to this day. So when it comes to uncertainty quantification, does it play any role in that discussion?
I think it may. Maybe not what I presented today specifically, but I think uncertainty quantification may play a role in defining or helping define mathematical frameworks for quantifying risk, right? I mean, if you talk about insurances as well, I mean, insurances is a big part of the discussion. How do insurances police their self-driving cars, or companies that use self-driving cars, right? There needs to be a mathematical framework in how you specify costs and risk. And I think uncertainty quantification tools can and will play a big role there. In fact, I was in touch with someone who was at an insurance company, and there was a discussion going in this direction. Now, in terms of accountability, and that's more what you hinted at, I'm not entirely sure if I I think if uncertainty quantification is done wrong, you may an engineer may be accountable, or a company or an insurance company, right? But yeah, I'm not sure if I have a clear answer there. I think we can provide tools to help assess risks, but who is to blame in these, let's say, delta percent of the bad cases? I'm not sure. Yeah.
Yeah, thank you so much. And of course, I could ask plenty of questions, but I will leave room for others.
Thanks. Yeah, on this point, yeah, Ron, you have a question?
Yeah, hi. This is amazing talk. I really enjoyed this. But I do have some questions. I'm also using conform predictions as like a verifiers for
Mhm.
prediction models like a safety predictor models. So
Mhm.
my question is, so now when I'm doing it, I use like more like split confirmed predictions to
Mhm.
guarantee like marginal safeties, but since our data is really tilted, so now I'm considering SLCP, so it's more like an input condition CP. My question is, when I'm doing this, I didn't really care about like changing non-conformity score functions. So I'm a little bit worried that when I'm comparing multiple candidate models for the same task, how can I avoid the non-conformity score choice itself confounding the comparison? So like, is there a way for me to disentangle this model is like more reliable from like this model happens to produce a score that is easier to calibrate tightly?
I think there was a lot in. Let me try to understand what you're doing. So you said you're using split conformal prediction, or another variant of conformal prediction.
Yeah, I am using class conditioned and input conditioned
Okay.
confirm prediction at the same time. Yeah, so
Okay.
but when I'm doing this, I did change a lot of variables in my
Yeah.
process. But one thing I haven't considered about before this talk is like changing my non-conformity score functions.
Yes.
Now I
Yes.
see
Yes.
there's the importance here. So I just want to make sure like non-conformity
Yeah.
score functions is not going to like confound with my results.
Yeah, I mean, it's tricky, right? Because I mean, you can fix your nonconformity score and then use different models, and then you can say this model works best for this nonconformity score. But there may be a better nonconformity score for the other model, right? I guess that's what you're saying. And
Yeah.
there are some papers that look into finding the optimal nonconformity score for a predictor that you may be using. So I think what you may want to, you can send me an email. I can forward some papers. So there are like 2 or 3 like minimum volume kind of conformal prediction papers. And maybe a different approach would be that you fix your 3 or 4 predictors that you have, and you then construct simultaneously the nonconformity score that gives you minimum volume for each predictor separately. And then you just take the minimum volume one among those. I think that would be another comparison that you can run, because
So
there the nonconformity score is not fixed. So you fix your predictors, right? And then
yeah.
you synthesize a nonconformity score in some sense, but ultimately you're synthesizing prediction regions that give you a certain 95% coverage and that have a certain volume, right? And you could then just compute the volume and make a statement about that. And you could compare both approaches. So if you just send me an email later, I'm happy to forward. There are 2 references I think that would be suitable. Yeah, that would be a high level idea, I guess. Yeah.
Yeah, thank you so much.
Yeah. Yeah.
I did have a question. from what I understood, it seemed that the calibration step required, a safety value from past trajectory. And when this property is sort of physical, you can just measure it potentially. But when that is something like, when this ground truth is noisy or contested, like if the system is deceptive, for instance, how can the approach handle that?
Yeah, I think this is one of the tricky parts. There are, from the conformal prediction community, there are certain extensions and tools that let you deal with it. But there's always some trade-off, right? You don't get it for free. In a way, just to make a simple case, if you know the bound on the noise that you're assuming, you can use some worst case or robust versions of conformal prediction that can account for that in some sense, right? So that's basically what you could do. So you would use your noisy data as your calibration data. You would apply these tools. You would need to assume some knowledge about the noise that you're applying, and the prediction sets that you have, you would inflate them to account for that. I think that's one high-level approach, and there are different variants that basically do the same thing, I would argue. There are also other variants that try to go around this. They also there's a lot of work on missing labels, but I don't think this applies here really. That's basically not a super clean answer, but I think there's a lot of room for looking into this further. Because the statistics community, they have certain tools to deal with these things, but I guess we as formal methods, as controls people, we need to understand them and apply them to the specific problems and instances. Yeah.
Okay. I think that is, for me, informative. So
yeah, so my main message is we should read more in statistics books, and we should be following that community a little more closely. That's what I'm trying to do, because they have a lot of tools. It's just sometimes hard to, it's like they have a lot of toolboxes and tools, but it's sometimes hard to really, because they speak a different language at times, right? But really trying to understand and use what they're doing. What we've specifically focused on is, I mentioned this already twice now, but robust versions of conformal predictions. And I was initially thinking about talking about this a little more, because mostly in this talk, we assumed IID data. But there are really powerful tools to deal with non-IID data, as I hinted at in this interactive setting, but more broadly, right? And it's quite interesting, because it applies to so many settings. If your test data is different from your calibration data, for instance, if cameras are different, right? If lighting is different, but also if you use synthetic data, like you use generative model to generate calibration data that is synthetic, but during deployment you have real data. So you have ways of actually dealing with that. The high level, again, is there's some trade-off, right? You either lose some confidence or you inflate your prediction regions, but you can reason about safety and add robustness margins. Yeah. Not answering your question, but giving some other answer, I guess.
I mean, yeah, I think, there's a lot of context that Colonel's kind of before.
Yeah.
Well, I thank you for this.
One other point, if I may, and I talked to one of our robotics people from USC, that was more, we're thinking about LiDAR or bearing-based measurements, right? And the question was, how do we get calibration data that has the ground truth? And in many robotics application, you can, through a motion capture system or through calibration, different calibration, sensor calibration, I guess, you can get ground truth data, quite accurate data through experiments. And then you could run all of what we've been doing here. But that, of course, that requires that for the system in hand, you have some some lab setting where you have actually very clean data that is not noisy or that has the ground truth, right? Through markers such as the ones you use for a motion capture system. I guess that would be the practical answer, that you need tailored calibration data, specific calibration data. Yeah.
Thanks. I'm wondering if anyone else has questions. Don't be shy. We still have 3 minutes.
If there's anything, just also feel free to send me an email. I'm happy to interact more.
She?
Oh, hello, can you hear me?
Yes.
Yes.
Oh, actually, amazing talk. It's the very first time I got hear something about temporal logic or conformal prediction. And first, I want to make sure I got the right essence of your works. Is it okay, and is it right to say you are mainly thinking about dynamic objects that governed by dynamic equations, and you are considered that when we are dealing with dynamic objects, we have some kind of black box prediction. We want to using this black box prediction as much as possible, satisfying some safety constraints. Do I got the
Yes.
right essence? Yeah.
Yeah, exactly. What I talked about today is all dynamic obstacles such as pedestrians. Yeah, exactly.
Yeah. And actually, before I ask my question, I have to say I agree very much. You say that we should read more statistic books because they have some useful toolboxes, but they speak different language. For me, I have a background of studying feature information in some other sense of mathematical quantification. I deal with how much information we can obtain in a localization scenario. And so I got to read some statistic books. So I wonder, have you ever considered, the conformal prediction, to me, it's more like another toolbox. We apply it to a black box prediction. But what's the statistic property of this conformal prediction toolbox? What statistic results we can get from this result output of the conformal prediction? Beyond a score, beyond a safety or general score, what property of this prediction we can get from that in the statistic view?
I think what this is all about is, it's all a rank argument, right? You have, in a way, k+1 IID random variables, and you do rank arguments over them, right? You want to sort them and rank them in some sense. So conformal prediction especially is just ranking them and then gives you probabilistic guarantees. If you zoom out a little, like I said, there are risk measures. So ultimately, you reason about some properties of the distribution of a random variable, right? This may be ranks,
Yeah.
which is quantiles at the end of the day, right? Empirical quantiles. But it may be, expected values over a certain quantile. I think that's what this is ultimately about. I'm not sure what connection there would be with Fisher information. Might be interesting to look into, but I'm not sure if I can make that connection. But ultimately, all uncertainty quantification tools, to me, they reason over properties of distributions. And since you use statistical data, you reason over not only the test data point, but the calibration data also comes in there. So questions of how much calibration data you need and so on and so forth. Yeah.
Okay, I got another question. What assumptions we have made on the output of the predictions made by like RN or LSTM?
No assumptions. That's the beautiful part. It's really model agnostic. You don't need to make any assumptions as long as you can push data through it. You want some form of data that has already in the past traveled through the LSTM. And gives you some information of how good it was. There's one assumption that you're not allowed to use the same data to train the LSTM and calibrate on. So your calibration data has to be independent of the data that you use to train your LSTM.
Okay.
But yeah, but that's like never train on test, right? I mean, it goes along those lines.
Yeah, there's some universal. Yes.
Yeah, exactly. So
okay,
So
interesting talk. Maybe I'll look deeper in that, and maybe I'll send another inquiry email to you. Very amazing talk.
yeah, I believe your contact information is public online. So if we have further inquiry, we could reach out, right?
Thank you everyone for joining.
Yeah. Thanks, Lars, for the great, really educative and comprehensive presentation. Thanks all for having been here. And additionally, stay tuned for the upcoming events. Also, you will do subscribe to the Luma page, and you will receive future invites. The next one is in September. So yeah, thanks all, and take good care. Farewell. Bye.
Bye everyone.
Yeah.